Hello guys, my name is Hayden Bird, and this is Physics 2, Lab 4, Circuits and Capacitors. The purpose of this experiment is to give us a chance to apply both of Kirchhoff's laws, that being the node rule and the loop rule, in order to predict how electric energy sources such as batteries, capacitors, and resistors perform in both series and parallel circuits. This will help us solve the problem of what tools can be used to predict the behavior of a circuit and measure the potential differences across each of them. In order to solve this problem, we will be using concepts such as the node and loop laws, the energy conservation equation, and the natural log version of the initial voltage difference. A brief run over of the results for the current. While I initially predicted the current was going to be at roughly 0.201A, the actual current was 0.2A, just barely off from my original prediction, based on the equations I used that I'll get to later. The reasoning why I use the physics principles behind the models is that the usage of Kirchhoff's laws allows us to measure the voltage and amplitude of an electrical current, and the energy conservation equations in each variant that will be discussed in the lab will allow us to determine the difference in charge across each of the circuits. I initially hypothesized that if I decrease the charge on the capacitor, then both the voltage and current would also decrease because they share a direct correlation in the energy conservation equation. This experiment was performed online, so all you need is a circuit construction which can be found online and a computer. The system is the wires that are within the circuit and each component of the circuit, and the surrounding is the atmosphere that the circuit is hypothetically a part of if it weren't performed online. The following are initial conditions that I use to calculate the electrical difference, such as change in voltage. You can tell that the total voltage difference is 0, which falls in line with Kirchhoff's law, and I also calculated the resistance at the 47 and 100 resistor marks, which I will get to in just a little bit. There are also unquantifiable equations on the circuit website, such as how thick the wires are or how fast the current is flowing, which were not given quantifiable values. Before I get into how I calculated my results, here are the results for my experiment. In the later parts of this lab report, I will detail on how I concluded and derived each of these values. While possible sources of error were not much because it was done on the internet, I concluded that a systematic error could be a potential glitch in the server or the code, which would skew the values of both the inputs and outputs if something were to be coded wrong within the forum. Sources of random error could be potential human error in measuring dimensions of the wire or not having prior experience with the online circuit builder website. First, I'm going to start off with the series circuit. You can see that I predicted a value of the circuit by taking the voltage and dividing it by the total resistance to get a value of roughly 0.201A. However, you can see by the ammeters displayed in the diagram that the actual current was 2.0A. It was very close to what I predicted. And when I flipped the ammeter, it did not affect the current because it still remains a closed circuit. However, when removing one of the ammeters, the circuit becomes open, which explains why the ammeter reading is 0. However, if you plug in a voltmeter on the openings of the circuit, you can see that the potential difference across the circuit was roughly 18 volts. Even though a circuit may be open, a voltmeter is still able to read the potential difference as long as it has 2 firm contact points within the circuit. Going back to how I was able to calculate the total voltage difference and resistance, for total voltage difference, it was expected to be 0 based on Kirchhoff's law, and you can see the voltage values for each of the points detailed in the experiment. You can see that the total from C to D and E to F equal the negative of A to B, and everything cancels out to be 0. Lastly, if you take each of these values and divide it at the current at that point, within that point, you'll be able to find the resistance for each of these specified points in the experiment. Lastly, we dealt with a series circuit based on how charges would affect how long a light bulb lasts. For the 10 ohm resistance, the light bulb had a shining time of 4.4 seconds with a discharge time of roughly 9.4 seconds. And for a charge with 20 ohms, we had a 7.1 second charge time with a discharge time of roughly 18.4 seconds. As for finding the time constant of other resistors, I was able to take a bunch of data points that I generated with a 30 ohm resistor and find a line of best fit using the equation of the natural log that we found in the very beginning of the lab. I was able to take the slope of the line by finding a line of best fit and take the negative of the inverse of that slope to find the time constant, which is negative 1 over negative 0.167, which gives us a time constant of roughly 6. Going back to my model predictions, one thing I was correct about was that the current and voltage would decrease if I lowered the charge. I hypothesized this because of their shared relationship in the energy conservation equation. And one thing that I did not expect to happen in the experiment was the voltmeter to be able to read an open circuit. This was because when I plugged the ammeter into the open circuit, it did read 0. However, it was able to have a measured value because it measures change of potential energy rather than charge itself. Moving on to the discussion questions, I'm faced with what if I was doing this in real life with an actual ammeter, what would be different, and how would it affect the circuits? So an actual ammeter, unlike the one online, has some internal resistance, so voltage would decrease throughout the system. Because of the energy conservation equation, we know that the circuits would have less voltage and less charge going through them, making the online simulation essentially impossible to replicate in real life. Now I'm asked if what if I used a real battery in the real life experiment with no resistor in the circuit, how quickly would the model predict the capacitor to reach full charge, and would this ever happen in real life? If you were able to apply this experiment in real life, the capacitor would take longer than expected to charge. Even though there is no resistor, the battery still has internal resistance, meaning the prediction would not happen, or at the very least, would not happen as fast as it is predicted on the online circuit builder. The ideal model would not predict it quickly for this very same reason. Thank you for watching my lab, and please be sure to like, share, and subscribe.